Good morning, everyone. Thanks for getting up early. So my name is Yalong. This work is collaborated with Tim Dwyer, Bernie Journey, Kim Marriott, Maxime Cordell, and Hao Hui Chen. They are awesome. So our paper focuses on visualizing origin-destination flows. There are many such data around the world, like migrations from one country to another, movement of animals, food, or even abstract things like diseases or knowledge. OD flow data contains geographic information of origins and destinations. It usually also contains other properties like quantity, for example, the number of migrants, and the direction, for example, from China to Australia. The most common way to present such data is using a flow map, and it is the focus of this paper. Flow maps use lines to connecting origins and destinations, and usually use thickness to present the quantity. According to the literature, geo-visualizations can be considered as two components, so the attribute space and the reference space. In terms of flow maps, we have these two components as flows and the underlying map. Let's look at the attribute space first. This is how to present the flows. Hand-drawn flow maps exist more than 200 years. They are intuitive and visual appealing, but takes time to create. To produce flow maps more efficiently, computer scientists start to create digital flow maps automatically. One natural way to map these flows is using straight lines connecting origins and destinations. However, this cannot scale to large data. To reduce the visual clutter, several algorithms create tree-like flow maps. They look beautiful and clear, but they are only applied to one too many flows. There is also possible misinterpretation of non-existent hierarchies. Edge bundling is a promising technique to present many-to-many flow data. It's easy to find the overall skeleton of the data. However, it's not easy to say individual flows. Recently, a fine-out style of flow map has been proposed. It maximizes the angular separation of flows at origins and destinations. This technique has been tested in a control user study, and it is one of the conditions we tested in our paper. These flow maps are all created in 2D space, and visual clutter is the main issue which affects the readability. Visual clutter basically is produced by putting too many visual elements in a limited space. So can we simply add more space to reduce the visual clutter? A natural thinking is using the third dimension to add more space, like what we demonstrate in this video. However, what is the best way to use the height remains unknown, so we explore different encodings for height. First, the height can be all the same. Height can also present quantity, in which case it's a double encoding. Quantity can be read by either thickness or height. Height can also present distance. The faraway pair will be on top, which we believe can better offset the flows. From the literatures, we understand 3D visualizations on 2D screens have a few limitations like occlusion, perspective distortion, and unnatural interactions. We believe in immersive environments, we can have accurate space tracking and real-time per-eye rendering, which makes the user easy to find the optimal viewpoint and manipulate the 3D objects easily. So we bring the flow maps into immersive environments. Another motivation of this research is the preparation for a future without physical screens. With the rapid developing techniques like VR, AR, we may no longer need any physical screens in the future. As demonstrated in this figure, in such case, how we should visualize data in the space around us. We can still create 2D visualizations in immersive environment. There is no problem. In terms of flow maps, we can have the basic straight line flow maps, which we call 2D straight. We can also have the state-of-art fine-out 2D flow maps, which we call 2D curve. We can also design and create 3D flow maps, as we discussed previously. An important question here is which one is better, 2D flow maps or 3D flow maps? We then conducted a controlled user study to compare them. We tested a task involving both search and compare operations, that is, find and compare two flows. We use leader lines to label the two pairs of origins and destinations, like demonstrated in this figure. We recorded time and accuracy. We are also interested in user interactions. So we recorded the view angle and the time spent in different types of interactions. Let's first look at the accuracy and time. In order to present accuracy and time in one single chart, we present the data based on a scatter plot. We present the 95% confidence interval as a point with arrow bars. Project the point to y-axis, then you will get the accuracy, and to the x-axis, and then you will get the time. Let's put all conditions in the scatter plot. We can say, in terms of accuracy, 3D distance is a clear winner. We then run some statistic tests, and of course, we got a lot of p-values. To present them more straightforward, we use a node link diagram. Here is example showing 3D distance is significantly more accurate than 2D straight with p-value equal 0.0185. Let's present all the significant results. We can say 3D distance is more accurate than most of the visualizations. Now let's look at the time. 2D straight is clear a winner in time. And then again, we run some statistics test, and the arrow here is similar to the accuracy, but here it is faster. We can say 2D straight is the fastest with statistic significance. We collect the view angles of participants from the study. 0 angle means looking at the map perpendicularly, while 90° means seeing from the perfect side. We plot the histogram to see the distribution. We also add median lines to this histogram, so we can say the median value of 2D flow maps is roughly 25 degrees. When it comes to 3D, we can say participants tended to look from the side more in 3D conditions. We then look at the interactions. We first look at the percentage of time participants moving their head in immersive environment. We can say it is similar across different visualizations. We then investigate the time they moving the maps, so they manipulate with 3D objects. We can say participants moving the maps more in 3D conditions than 2D ones. As we discussed before, flow maps can be divided into 2 components. We have just discussed about the representation of flows. Now let's look at the reference space. Maps have been used everywhere. However, a map is unfolded from our 3D planet. This unfolding process is called map projection. It has been proved that it is not possible to unfold the Earth without any distortion. Furthermore, there is another problem. Let's have a try. If a plane starts at A, following the direction, keep the direction of flying, will it reach X or Y? If you think it will be X, please raise your hand. Sorry, you are wrong. Don't worry, there are many people who will misread because the map ages. You think you are following the direction, but the correct answer is Y, because it will reach the other end of the map. This has been investigated by researchers. As there are known issues for map projections, we explored different visual presentations of maps in our previous work. Check out our EuroVis paper for more details. In terms of flow maps, instead of creating flows on a flat map, why can we not using the flows on top of a globe? We did not stop there. We want to explore is there any other design alternatives. Inspired by our previous work on MapTrix, which uses 2 maps to present origins and destinations respectively, we placed 2 maps in immersive environments and linked them from origins to destination. People, not just me, really like to manipulate these 2 maps in immersive environments. They are actually much more active and passionate than I did in this video, but you know, I'm a bit shy. So you may notice that the center of the previous map looked different than that one. This is the interaction we introduced to immersive environment, what we call georotation. We know a map is unfolded from a globe, as we just see the video. Everyone likes rotating a globe. How about we unfold the globe now? We get a very different map. And actually, we can do this interactively. Imagine you are dragging the red dot about the map, and this is how it looks like as you're rotating the globe. Let's put the flows on top of it. You can see the flows will change in real time, especially when the origin destination across the edges of the map. We believe georotation can be a compensation of distortions and discontinuity of maps, as the user can interactively change the part of the distort and the edges of the map. An obvious limitation of a globe is the limited of field of view, as the user can only see half of the globe at one time. We believe with the ability to rotate the globe easily, users can have a temporal memory of the part they cannot see at one moment. We conducted another user study to compare flows on different reference space. We again record the accuracy and time, as well as time spent in different types of interactions. Let's look at accuracy and the time first. We can see globe is a clear winner in accuracy, and we run some, there is some error with the image, but anyway. We found the globe is significantly more accurate than 2D straight and maps link. In terms of time, we can say maps link is obviously slower than others. Statistic tests align with the result in the chart. We then look at the interactions. We can say the time of head moving is similar in all visualizations. When it comes to the move the map, we can say that people do not like to move 2D straight at all. As I said, people really love to move maps links in immersive environments. In this study, we have a new interaction, georotation. We can say participants like to rotate both the 2D straight and globe in immersive environments. We further investigate the possible benefits of georotation. We found with georotation, 2D straight become more accurate, but it also takes more time. In order to explore the upper bound of the scalability, we tested the 3 visualization in large data set in another user study with 200 and 300 flows. I promise this is the last user study. So globe is the winner in both accuracy and time very clearly. We then look at the interactions. Similar to the second study, we found the head moving is similar in all visualizations. Again, very similar to the second study, people do not like to move 2D straight at all in immersive environments. In terms of georotation, people spend a lot of time rotating the 2D straight maps. Here, we generate some high-level takeaway messages, but please check our paper for more details. We think globe is the best option for global flows. If we want to show a regional flow, for example, an interstate migration in Germany, we should use 3D distance. If you really need to use 3D, you use 2D. You can add georotation interaction 2D flow maps. Here's the image with labels of all the co-authors. We all believe with the envisaged collaborative thing in this image is a possibility of VIS meet immersive technologies like AR, VR, and MR. Okay, thank you. I'm going to play the last slide a little bit later, but I'd like to take any questions.